Without further ado, it is my great pleasure to introduce Monsieur Philippe Nadeau, who is giving his DDS today. Philip comes to us originally from ETS, pardonnez-moi, um, and came over to UTIS, started with his master's, and then made the um, incredibly prescient and ideal life choice to continue on to a PhD. And now is at the end of that journey. We can ask him at the end how he feels. And so he's done some really great work. He'll tell you all about it in inertial parameter estimation and also stable object placement planning and contact robustness to perturbations and forces and so on. I will let him tell you that. I would be remiss also not to mention, though, that Philippe is an excellent person in the lab. In part, amongst other things, he has installed our force torque sensors, built our experiment tables after designing them himself, actually, and assembling them, assembled electronics for the control and power box for one of our robotic arms, and many other things. And for this and for other reasons, he received our Lab Service Award last year. So, if you would like to stay on as a postdoc, please let me know because otherwise, I'm not sure how we'll fix anything that breaks. But so it's been a great pleasure. I will stop talking, and Philip, whenever you're ready, take it away.
Cool. Thank you so much, John, for the introduction. All right. So I think everything's set up. Okay. So I assume everyone can see my screen.
Looks good.
So hello, everyone, and thank you for being here today for my doctoral seminar. Hopefully, by the end of this short presentation, you will have a better idea about where I have been hiding and what I've been doing in the past 5 years. So I debated whether to include an overview slide or not, but I decided to make one since my good friend Adam Hall loves them so much. And so in this presentation, we will first briefly cover the context in which my research work is situated. We will then look at two methods for the efficient identification of inertial parameters of objects manipulated by robots. This capability will allow robots to compute the robustness of multi-object assemblies. So we'll see what robustness is and how it can serve as the basis for decision-making algorithms. We will cover two methods that uses robustness to decide how to place an object in a stable manner in a given scene. And while the first method is purely geometric, the second relies on machine learning. So that's the plan for today. So this thesis is developed in the context of the Canadian manufacturing sector that is largely composed of small and medium businesses. According to surveys, labor shortage is an important issue, and these enterprises would like to use robots to alleviate the problem. However, the lack of skilled robot operators and difficulties in integrating robots with other processes are some of the main obstacles encountered. So in short, businesses in the manufacturing sector are looking at robotics to increase their efficiency, but require versatile and autonomous robots. So in this context, my PhD work focused on developing algorithms, improving the capability of mobile collaborative manipulators in perceiving, modeling, and acting autonomously in their environment, particularly in the context of object handling tasks. And most of my work focused on efficient physics-based methods applicable to general rigid object environments. So I have proposed algorithms improving the capability of robots to quickly identify the dynamical properties of manipulated objects. Crucially, I developed an algorithm modeling the robustness of general rigid body assemblies to external forces. And I showed how this dynamical model can be used in planning to stably place objects efficiently, a very hard problem that had no practical solution. And so in this presentation, I will give an overview of each of these solutions. But before diving into the details of these techniques, let me illustrate with an example the type of problems we would like to solve. So we have an autonomous mobile robot that is responding to high-level commands. In the first step, the robot moves to a conveyor to pick up objects. Since no human worker is around, the robot can use its sensors at full speed to identify object shape and inertial parameters. Then the robot has to move to the second stop as quickly as possible while ensuring that objects remain stable on its tray. At the second stop, the robot has to operate slower since a human worker is around. The third step involves placing objects on a cluttered shelf among other objects. And finally, the robot can dock to a charging station and wait for new directives. So some of the questions that the robot needs to answer include, what is this object? How fast can I safely transport this assembly? Can I lean this object on this other one? Or is it safe to move close to these objects? And this thesis provides tools to help the robot answers some of these questions. Specifically, this thesis considers the problem of autonomous object handling with collaborative robots, which requires placement planning and efficient transportation capabilities. These are enabled by a sound assessment of assembly stability, which in turn depends on efficient inertial parameter identification. And so this thesis consists in a vertical integration of contributions addressing three key elements of the problem. Now we'll now give a brief overview of each contribution before diving into more detailed explanations. So the first contribution consists in a method whose objective is to reduce the impact of low signal-to-noise ratios when the manipulator is moving slowly, while still enabling accurate identification when the robot is moving faster. So in this work, we observe that gravity dominates other forces acting on the object during collaborative operations, and that using a reduced dynamics model can alleviate some of the identification problems. So in this work, we will combine the reduced model and the complete model or full model through a weighting scheme that I will describe later on. The second contribution stems from the observation that artificial objects, especially industrial tools, are typically built from a few parts of homogeneous density. So in this work, we perform a visual part segmentation of an object to divide it into a few parts. And then, assuming that parts have a homogeneous density, we reformulate the problem into a simpler one, such that the identification can be done safely through stop and go motions. And in this presentation, we will explore how this can be done. The first two methods that I will present enables a robot to define models for the objects it interacts with. But the other methods that I will present consider what can be done once these models have been determined. So first, we will explore how the knowledge of these object models can be used to assess the robustness of rigid object assemblies to external forces. In other words, answering the question, what forces can objects withstand before becoming unstable? The last part of this presentation will consider the problem of efficiently finding stable poses when placing an object in a scene. So in this work, I show how my robustness criterion can greatly improve the efficiency of stable object placement planning. In a nutshell, this technique is based on considering contact points instead of poses when planning, and I'll tell you all about it later in the presentation. So zooming out a little bit, my research work addresses the problem faced by mobile robot manipulators, particularly in the context of sharing space with humans. In such contexts, robots often have to limit their speed to reduce potential forces in case of collisions. And this is referred to as collaborative operations. However, this strategy hinders the identification of inertial parameters of manipulated objects because it forces robots to use signals with low signal-to-noise ratios. And typically, these parameters are determined through an identification trajectory that is clearly unsuitable for collaborative operations. So the inertial parameters of an object include its mass, its center of mass, and its moments of inertia. Identifying these parameters allows robots to precisely manipulate objects that are initially unknown, making it an important capability to have. More specifically, an object's inertial parameters appear in its equations of motion, linking the observed forces to its kinematics. And by studying the signal-to-noise ratios of each term in the equations of motion, we observe that some of them become very small during collaborative operations and are therefore the source of inaccuracies in the inertial parameter identification. So this is one of the first challenges that I addressed in my research. And to mitigate this problem, I proposed two different solutions. In the first solution, I define a reduced model of the dynamics that assumes that gravity is the dominant force acting on the object. The key element is that the reduced model does not include those terms from the full model that contribute low signal-to-noise ratios during collaborative operations. And so this reduced model is combined with the full model through a weighting scheme, which depends on the magnitude of the velocity and acceleration signals. And so in short, during collaborative operations, the reduced model guides the search for inertial parameters, while the full model is kind of blinded by low signal-to-noise ratios. But when the robot can go faster, However, the weight of the full model goes toward one, and the robot uses the complete dynamical information to perform the identification. So in this work, performing experiments with real robots and real objects can be challenging because we need ground truth values for the inertial parameters of the objects, but these cannot necessarily be easily measured. So I designed and built a modular test object that is composed of a 3D printed frame in which weights can be precisely placed in a great variety of configurations. And so for each tested configuration, I attached the test object to the force torque sensor of the robot before performing a short identification trajectory. And the results from both simulation and real-world experiments suggest that our method converges much more quickly than other methods during collaborative operations for which the average speed shouldn't exceed 0.25 meters per second as per the ISO standard. Our algorithm is also much more robust to noise in the data and produces more accurate results when the noise is moderate or high. So in short, the takeaway from this work is that in robotics, choosing an appropriate dynamic model is always a very important decision to make. So while the method that I just previously described strives to make the best use of the available data, I also developed a method that tackles the problem by integrating new data, namely visual information about the object. This method is based on the key observation that industrial tools are usually built from a few parts of homogeneous density. So in this work, part segmentation is done on point clouds in a two-stage process, where the first stage performs point clustering based on local features, while the second stage performs volumetric segmentation that optimizes for part convexity. By segmenting the object into parts, the problem of identifying the inertial parameters can be reformulated into the one of identifying the mass of each part. And doing so enables identifying all inertial parameters accurately with safe stop and go motions and with the added benefit of seamlessly dealing with articulated objects. So to test the full pipeline, so not only the identification, but also the segmentation, I built a data set of 20 workshop tools with for each object a watertight mesh, a labeled point cloud, and the true inertial parameters according to CAD files. Compared to baselines, my method outperforms other algorithms for the identification of the center of mass and the inertial matrix when signals are noisy. So to demonstrate the accuracy you can get with this algorithm, we have a robot equipped with modest hardware, perform shape reconstruction, part segmentation, and parameter identification of a hammer. And then the robot is able to balance the hammer on a very small peg. So in summary, identifying inertial parameters is important because they connect kinematics and dynamics through the equations of motion and can therefore enable precise object manipulation. With collaborative robots, this can be challenging, and I proposed two methods to improve the accuracy and identification speed. The first method adapts the dynamics model to avoid low signal-to-noise ratios, while the second method makes use of robot vision to bring in new information. And so for the rest of this presentation, we will assume that we're equipped with methods that can provide us with accurate object models. Now, in many activities of daily living and also industrial tasks, we're dealing with assemblies of multiple objects that are in frictional contact with each other. And robots could really benefit from the ability of assessing the robustness of rigid object assemblies. That is the capability to answer the question, what forces can objects withstand before becoming unstable? And motion planning applications include avoiding moving too close to objects that could easily topple and transporting an assembly as quickly as possible without destabilizing it. Task planning applications include enabling a robot to plan decluttering or disassembling operations, as well as stable placement planning. And my work provides the first efficient robustness assessment method that can be used with any assembly of rigid objects. So we're interested in the force that would trigger a relative motion between objects in an assembly. And I will now present my algorithm to obtain it efficiently. So we model an assembly with a contact interface graph in which objects are designated by nodes, while edges represent the contact interface between two objects. With this representation, the onset of instability can be modeled as a graph cut, which will separate the graph in two subgraphs. When the relative motion at the interfaces cut is translational, slipping happens. And when the relative motion at the interfaces cut is rotational, then toppling happens. And we recognize that these two situations can be treated separately. And so that's what we do. And we combine their results at the end. So let's start by focusing on the robustness of an assembly to slipping. So to do so, we first assign to each edge of the contact interface graph a capacity corresponding to the total traction of the corresponding interface. We then designate the object on which the force is applied as the source and the fixed support, like the wall or the floor, as the sink. With this structure, the assembly's robustness against slipping can be efficiently computed using a maximum flow algorithm. While the maximum flow determines the robustness of the assembly, the minimum cut that is obtained at the same time defines the subset of objects that will first slip. Similarly, toppling can be modeled as a cut in the graph, minimizing the cumulative robustness of the interfaces cut. In this case, we start by considering some cut in the graph. Then we compute the convex hull over the contact points on the interfaces cut. Edges of the convex hull defines axes about which toppling can happen. For each axis, we determine the force that is needed to compensate for the torque exerted by the contact points about the toppling axis. And the process is simply repeated until all graph cuts have been considered. So after having dealt with the translational and the rotational situations, we can now combine their results. And this is quite simple, in fact, because the force that will trigger instability is the weakest between the one triggering slipping and the one triggering toppling. So here we define the robustness to an external force in direction E hat applied at point P to be the minimum between the slipping and toppling robustness. It can be especially useful to compute the robustness to normal forces applied at surface points on a given scene. Here, a cube on top of another cube. We can visualize the result with a color code where lighter colors closer to yellow indicate larger robustness values and black indicating infinity. We can compare my method to simulation-based and optimization-based methods in terms of speed and accuracy. To do so, we consider three simple scenes and use the different methods to compute the robustness to normal forces applied at surface points. So here on the left, we have the simplest possible scene, a cube on a floor. In the middle, we have a stack of three cubes defining a serial kinematic chain. And on the right, we have a table defining a simple parallel kinematic chain. These simple examples are convenient because we can manually generate ground truth solutions for them. It would be much more difficult to do so with more complicated examples. According to our results, the simulation-based method is quite slow and also quite inaccurate, especially with the table scene. The optimization-based method is already much more accurate, but is very slow. In contrast, our method produces a much more accurate result and does it much faster in all cases. So this work can provide a foundation for autonomous decision-making when interacting with objects in frictional contact. So for instance, my method can be used to determine the maximal acceleration that can be sustained when transporting a set of objects. My algorithm can also enable a robot to define safe disassembly sequences autonomously. So in summary, when calculating the robustness of multi-object assemblies in frictional contact, we asked ourselves what forces objects can withstand before becoming unstable. And assuming that objects are rigid and known, we represented the assembly as a contact interface graph, and then defined an algorithm to operate on the graph, such as to compute the maximum force that can be applied in a given direction on a given point of the assembly. We ultimately showed that the performance of this algorithm are much better to that of other methods, and we highlighted concrete tasks for which robustness can be valuable. There is another task for which my robustness assessment algorithm can be useful. This task is stable object placement planning, a task that is frequently done in a variety of environments. Stable placement planning is very hard due to the fact that a valid placement must be in contact with the scene, yet should not penetrate any object, while also resulting in a force equilibrium. In essence, a very small proportion of the poses in the workspace will result in valid placements, making existing methods highly inefficient. So for instance, if you were to randomly select an object position and orientation in the workspace, the odds of selecting a stable pose are very, very small. Likewise, a method based on exhaustive search, would be extremely slow. Now, acknowledging that sampling over the space of poses is doomed to be highly inefficient, my work proposes to consider contact points in the first place instead of considering them only at the end. So the problem is reformulated into the one of finding contact points in the scene and on the object that result in a stable placement after mating the object to the scene. However, this strategy cannot guarantee that the selected pose will result in a stable placement, and a validation step will always be required. So finding a candidate placement starts by selecting 2 points on the scene with odds proportional to their robustness. The maximal odds are capped by Q, a cap that is exponentially decayed with every failed iteration of the planning algorithm. So in the limit, all points are considered with equal probability, but initially, more robust points have way more chance of being sampled. Now, points are also sampled on the object such that the distance between the points matches the one between the scene points, and such that the object can be afforded by the scene. So with 2-point pairs and with the surface normals known everywhere, all the degrees of freedom of the object can be constrained and a placement pose can be determined. So my method is compared to existing approaches in terms of success rate and average planning time on the task of finding a stable placement for a cube in a variety of scenes. My approach is 8 times faster than HM, while also achieving the best success rate. HM is a state-of-the-art searching method that also integrates placing heuristics. Just because we all love real robot videos, let's take 2 minutes to see our algorithm in action. This is actually a harder version of the problem where the robot has to select not only the pose for the object, but also the order in which objects are placed. So here, the robot will actually make a bad decision here by placing this object upside down, if you will. And the robustness on the sides of this objects is very low, as indicated by the bluish color. And this will almost create a toppling situation when placing the last object. So this last object has very, very little robustness. Very small force could make the second to last object topple. And as you will see, this will almost happen right now. Yeah. But nothing toppled, so all good. So thank you, Miss Ada. Ada is the name of the robot. Always say thank you to your robots, even if they're just LLMs. Okay, so to further improve the planner's speed, we turn our attention to the use of neural networks. However, since it's impossible to guarantee in advance that a placement will be stable, it's necessary to use generative models capable of producing a variety of placements for the same given scene. And in this work, we used a diffusion model. A diffusion model is a model trained to generate elements from a model distribution. So the training is done in two stages. In the first stage, a sample from the distribution to be modeled is iteratively noised using very simple equations such that the original distribution is transformed into a normal distribution. In the second stage, the neural network is trained to remove the noise and recover the original sample. Each denoising step can be interpreted as a movement in the data space. The direction of the movement is partly determined by the neural network, but is also influenced by a random element that allows for adequate exploration of the space. Once trained, the model can be used to generate elements from the modeled distribution. And doing so is actually quite simple. We sample from the normal distribution and pass these samples through the denoising process. And if you have any other questions about diffusion, I'm happy to see that my good friend Miguel is on the call, so he'll answer all of your questions. Now recall that the goal is to generate stable placements in an arbitrary scene. And in this work, four scenes are defined along with a large number of examples for each scene. A diffusion model is trained on three of the four scenes and tested on the fourth. So in fact, four different independent models are trained, and each model is tested on the scene that was not part of its training data. And here the task is to place a cube in a stable manner in the scene. So once trained, the model can be used to generate placements in unseen scenes. So this is a visualization of the object's trajectory throughout the denoising process for 10 placements performed in four scenes. By observing the generated placements, we can see that some of them are not very smart and will likely result in instabilities. For example, by placing at the wrong end of the cantilever, or at an edge of the table, or far from the center of the balance. To address this problem, a guidance term is introduced that is active during the generation of the placements. This term is added to the learn direction to steer the process toward another objective. Since this term is not directly involved in the denoising process itself, it's not necessary to retrain the model to benefit from guidance. In the context of object placement, the guidance direction can be used to encourage the use of robust supports to hold the object. So here we define the guidance direction as the one to follow to maximize an objective function that favors the object points being supported by robust points in the scene. So here again, the assembly robustness that I defined previously is used in the context of learning-based placement planning. The impact of guidance is clear. The object is more often placed in locations that promote the scene's stability while imitating as much as possible the placements provided as examples during training. A comparison between the placement distribution obtained without guidance to the one that is obtained with guidance clearly shows that using guidance leads the model to generate placements with a higher likelihood of being stable, even in scenes that were not part of the training data. And our quantitative results support this as well. The use of guidance reduces the time needed to find a stable placement and results in scenes that are more robust to disturbances. Now let's take a moment to review the main points of my work. Manufacturing companies need efficient solutions that require minimal supervision and can be easily integrated into a wide variety of industrial environments. My work fits within this vision by proposing modeling and planning algorithms aimed at improving the efficiency of interactions between robots and their environment. We have explored new techniques to identify the inertial parameters of manipulated objects, which has enabled the computation of multi-object assembly robustness against perturbing forces and the planning of stable placements. Finally, we've seen how physics can guide machine learning in generating solutions that are consistent with the natural world, a particular interest of mine. So I'd like to end this presentation by stating that a PhD can be a lonely adventure, but that I was extremely fortunate to be in a very welcoming and supportive environment. I'd like to thank everyone in the vast network of people that supported my journey and who contributed to make it fun and rewarding. And with that being said, I'd like to answer any question you might have. I believe we have a few minutes left.